We continued looking at our interaction gauge theory with interactions. Basically, we are looking at scalar Q quantum electrodynamics. Scalar in the sense that we didn't yet introduce fermions, so all the particles interacting electromagnetically in this theory are scalars. We calculated the propagators and various factors, the propagator for the photon, the propagator for the scalar. But this time the difference is, before we were always looking at real scalar fields, now we have complex scalar fields. So the main difference is now for the complex scalar field, we have both particles and antiparticles. So the Feynman, the propagator, has a direction for the flow of particles, which we showed by these arrows. And then we also had these vertices with momentum. And then we had seen that if you take any vertex, and if you just make sure that the momentum flow and the particle number flow are in the same direction, meaning that you have the freedom of just changing the direction of any form momentum, as long as you also change the momentum by minus itself, like here. For example, here I have a particle with momentum p1 coming into my vertex. I can say that it is the same thing as an antiparticle with momentum p1 coming into my vertex would be the same thing as a particle moving away from the vertex with momentum minus p1. All four components should change sign, including the zero component. So with this convention, if you just make sure that at each vertex, the momentum coming and leaving, they are in the same direction as the particle number flow, then for each vertex, what we have is minus I lambda. Lambda is the coupling strength times the sum of the momentum. In fact, here the lambda will be just the electric charge, 1.6 times 10 to the power minus 19 Coulomb. And then we also had this four-particle vertex where two photons enter, one scalar line enters and one scalar line leaves. And here the corresponding vertex factor is I times lambda squared. Now we were looking at this electron scattering. Basically, it is due to the exchange of a photon. So we draw all the lines, we put the momentum, and then we obtain the S matrix element. This is essentially our S matrix element. What we have is, now I'm not here calculating the 4-point function, because if you remember in the midterm you were asked to calculate the 4-point function from which you were supposed to calculate the S matrix element. Here now I'm directly calculating the S matrix element. So these basically tell me that for an outgoing photon, I have its polarization conjugate. For an incoming photon, I have just the polarization of the photon. These tell me that, these ones actually, any incoming or outgoing scalar particle, I just have one in my S matrix. So if you look at this diagram, the corresponding contribution to the S matrix will be 1 for this outgoing scalar particle, 1 for this incoming scalar particle, 1 for this other outgoing scalar particle, and another one for this one. So these are just ones. Then I have this vertex factor. It's minus I lambda times all the momenta at that line is in the same direction of the particle flow. So I have minus I lambda P1 plus K1. Similarly, for the other vertex, I have minus I lambda times P2 plus K2. Then I have the photon propagator, which is all this expression. So once I see the Feynman diagram, I can straight away write the corresponding contribution to the S matrix element from this diagram. Now, another thing we noted was if you just take any one of these vertices, multiply it with Q mu, it's exactly 0. But this is nothing but the word identity. Well, in this case, it is kind of trivial. The reason why you have this satisfies the word identity is both the incoming and the outgoing electron lines are on shell. So here, when we wrote the word identity, we just get the the mass of one squared minus the mass of the other squared, but they're both the same particle, so their mass squares are the same if they are on shell. And so we get 0. It's not always so trivial. Now we will look at, today we will continue with this discussion of the electron scattering of electron in the scalar QED. We will also look at electron-positron annihilating into two-photon processes where the word identity will not be so trivially obtained. Still, we will have the word identity. It will be satisfied, but the reason why it is satisfied won't be so trivial. So you see here, this derivation actually proves that if the lines connecting to the vertex, the scalar lines connecting to my photon vertex are on shell, then word identity is satisfied, at least for that momentum, as no matter what happens in other places in the diagram. You see, I can have much more complicated diagrams like...
Could you roll up? More, please. The upper part, still the upper. Yeah, for example, in the I lambda square case, there, I mean, 2 photons and 2 electrons, yeah, that is. In this type of diagram, the word identity is satisfied there?
No, you see, word identity has to be satisfied for the matrix element, not for the diagram. You see, in this case, you see, what we have seen is here, the word identity is satisfied per diagram. It's not always the case. It doesn't have to be the case. The matrix element has to satisfy the word identity. In fact, that is why one of the reasons why I will be looking at this diagram, because each one of those diagrams will not satisfy the word identity. In fact, if I don't include this term, word identity is not satisfied. So if you remember, one of you were asking, since this term in the Lagrangian was lambda squared term, and the other interactions, other vertices like here, they are proportional to lambda, can't we just ignore it saying that it is very small? The answer is no, we cannot. Because that term, that lambda squared term, although will be smaller, it will be crucial for the word for gauge invariance. That we will see. And in fact, for example, I can imagine such diagrams in scattering. And you can just write much more complicated diagrams if you like. I don't care. The word identity is still satisfied mainly because of just this vertex. If the incoming particle and the outgoing particle, they are on shell, the word identity will be satisfied, at least for this photon. For that photon, there will be word identity satisfied, because remember, the photon propagator contains these terms proportional to psi, which is an arbitrary parameter, arbitrary Lagrange multiplier, and word identity is crucial to show that the final result at the end will be independent of psi. But of course, again I repeat, just because this vertex satisfies word identity for this momentum over there doesn't mean the word identity is satisfied for this diagram. Because you see, word identity have to be satisfied for all the momenta of all the photons, including the momenta of this one. So the general proof will be difficult with this approach. Well, somewhat doable, but we will discuss shortly what is needed to be done. Now, any questions up to here? You see, these Feynman diagrams are just like kind of a jigsaw puzzle. You have the pieces. In our scalar QED case, we have these vertices. You have these lines that might be connecting vertices, and also these lines connecting vertices. And then we can have incoming lines, outgoing lines, both for the scalar And for the vector particle, let me also add the momenta. Well, this part of the jigsaw puzzle basically gives me minus I lambda P1 plus P2 mu. This part of the jigsaw puzzle corresponds to I over P squared minus M squared. If you have such a piece in your jigsaw puzzle, again, this corresponds to I over P squared minus G mu nu plus 1 plus psi P mu P nu over P squared. And both of these, this one and this one, they just correspond to factors 1. And these lines, this one, let me say this is the mu. This will be epsilon mu, this will be epsilon mu star. And basically, just knowing these, we are able to calculate any contribution to any process at any order. So for our process E minus E plus scattering into E minus E, no, E minus E minus scattering into E minus E minus, what we need to do is, this is our black box, this is E minus, this is the other E minus, this is E minus, this is the other E minus in the outside. So the question is, this is my black box. How can I fill my black box using these parts? These are the pieces of my jigsaw puzzle, such that I will be able to connect the incoming lines to the outgoing lines somehow. So that's the question. And well, it's like, again, solving a puzzle. So if you have an incoming line, it should definitely have, it can only be attached to a vertex. But from the vertex, there has to be another outgoing line. So it can be this electron, the outgoing electron. And similarly for the other electron. And those two the vertices will also be connected. This is one contribution. Well, I can have the other contribution. You see, the topmost electron line comes. It has to be attached to a vertex. There has to be a line coming out of that vertex, but that line can be the outgoing electron, but the other one. And similarly for the other line. So this is the other diagram that I can imagine. You can write as many diagrams as you like, as complicated as you like. All of them will contribute at the given order. At the lowest order, with the minimum number of vertices, I just have these two. And I don't have any other diagram. Question? So let's just calculate the corresponding terms. I have written down what we are trying to calculate will be what's the cross-section for this process, because that is what we will be able to measure. Because basically, cross-section will tell us the probability that the electron in the final state will be scattered in some direction or in the other direction. So we can measure that probability by just colliding many electrons and just putting our detectors and see how many electrons we get in a given direction or in the other direction. That will be proportional to the probabilities. So that's the experimental measurement. And here now we can calculate the theoretical probabilities through this cross-section. So let me just write the momenta, P1, P2, K1, K2. You see, this is my jigsaw puzzle. It is made up of many different parts. So what I need to do now, just multiply the corresponding mathematical expressions for each part. You see, here I have an incoming line, incoming scalar line. If you look back to our Feynman rules, you see, for incoming and outgoing scalar lines, the corresponding factor is 1. So I have, for this one, I have 1. For this one, I also have 1. For this one, again, I have 1. And also for this one, I have 1. So I wrote the corresponding factors for each one of the incoming and outgoing lines. Now I have a vertex here, which has, this is P1, K1. The momentum of the particles is P1 and K1. So the corresponding vertex factor will be minus I lambda P1 plus P2. Well, vertices, they also have a Lorentz index. So let me just put, so this is the Lorentz index. The other vertex also has a Lorentz index. So here I have another vertex where the incoming and outgoing momenta are P2 and K2. No, sorry. This is K2, this is K1. P1 plus K2, no. Yes, P1 plus K2 mu. Then I have another vertex over here. The corresponding contribution is minus I lambda P2 plus K1 nu. So there's just a single part left whose contribution I didn't write down yet, and it is this photon propagator. Well, the photon propagator is I over P squared minus G mu nu. I don't write the, no, not P, sorry, Q. I don't write the Q mu Q nu term. I have already seen that that gives me 0. But if I would like to show, for example, the Lorentz invariance, psi independence of the result for a general diagram, I should also include that term and calculate and actually prove that it is 0. But for this diagram, I already did that. And so this diagram is minus lambda squared. And I have P1 plus K2 times P2 plus K1 divided by Q is, by the way, P1 minus K2 squared. So this is the contribution.
There is I.
Yeah, there's an I. This is the corresponding contribution to my matrix element from this diagram. At lambda squared order, I have this other contribution. This is P1, K1, P2, K2. Well, basically I have the same ones will appear. Let me not write it down. And then I have this vertex, let me call that vertex mu, this one nu, minus I lambda. This time it is P1 plus K1 mu. For the other vertex, I have minus I lambda P2 plus K2 nu. Then I have the photon propagator I over Q squared minus G mu nu, which will be minus I lambda squared P1 plus K1 P2 plus K2 divided by P1 minus K1 squared.
Also, instead of minus, you have to get plus.
Because of that minus G mu nu. Yeah, you're right. So my invariant matrix element for this process is I lambda squared P1 plus K2 P2 plus K1 over P1 minus K2 squared plus P1 plus K1 P2 plus K2 divided by P1 minus K1 squared. Now, quite often when we have this two-particle scattering, we don't express things in terms of the momenta, but rather what we use are the so-called Mandelstam variables.
The denominator said we write, for example, in the first case, P1 minus K2.
No, P1 plus K2.
P1 minus K2.
Ah, the Q.
Yeah, Q part.
Okay.
But there is other part also, P2 minus K1.
Okay. You see, P1 minus K2 is equal to K1 minus P2.
Direct, okay.
I have four momentum conservation.
Doğru. Sure.
You should integrate for Q, right? Integrate.
Why?
Because it is between
But you know, the value of Q is fixed
things.
by the initial momenta. It's not free. You see, if I am the one creating the initial particle, so I know their initial momentum. So I know P1 and P2. I measure the final particles. I know K1 and K2.
But Q doesn't know E over Q squared.
Q knows. You see, here I have, you see, if you remember our initial definition of momentum space Feynman rules, what we had obtained was we had basically arbitrary momenta for each one of those lines, each one of the propagators, let's say. But then we also had four momentum conservation at each vertex. If we use the four momentum conservation, and you are right, in that case, we do have integral over Q with a Dirac delta which conserves a four momentum at that vertex. So I can integrate, I can evaluate the Q integral using the Dirac delta function. So what is usually done is you don't write the Dirac delta functions in the vertices. Every vertex has a momentum conserving Dirac delta. But you don't write them down. What you do is you just make sure that you define your momentum such that at each vertex momentum is conserved. If there is any momentum whose value is not fixed by the initial or the final momenta, then those integrals still remain. You have to integrate over all of them. But here, if I know the initial momentum and the final momentum, there's no, Q is fixed. I know what Q is. There's no integration there. So what are the Mandelstam variables? Well, there's the T, which is P1 minus K1 squared. You see, these Mandelstam variables, okay, if you can't remember which one is S, which one is T, which one is U, just let's look at the diagrams for this process. With some imagination, you see, there is this diagram. There's such a diagram where the initial electron and positron annihilate, create a photon, which then creates the final electron and positron. Okay, now you need to use a bit of fun imagination. This is an S. What is the momentum of the photon? Well, the momentum of the photon is P1 plus P2. So the S variable is defined as P1 plus P2 squared. If you look at this diagram, again with a bit of an imagination, it's a T. What is the momentum of the photon? P1 minus K1. So T is P1 minus K1 squared. There's just a single combination left that we didn't define. There's P1 minus K2 squared. Now we don't have any more imagination. S, T, the next letter is U. So this is called U. And again, keep in mind that we have four momentum conservation. So T can also be written as P2 minus K2 squared. S can be written as K1 plus K2 squared. And U can be written as P2 minus K1 squared. At least this is how I remember which one is S, which one is T, which one is U. So let's go back to our invariant.
Say like that, you know, K1 equals K2, then can we say that T and U variables are equal to each other?
If K1 is equal to K2, yeah, but in general they are not.
Yeah, in previous lectures, you know, we relate the, like, somehow I just thought, you know, we say that T and U, I don't know, when we draw in the Feynman diagrams, they're equal to each other or something. So I just trying to understand that part.
No. Well, let's see. In terms of these variables, if you look at this one, I have such cross terms. What do I have there? I have P1 plus times P2. But P1 plus P2 is 1 over 2 P1 plus P2 squared minus P1 squared minus P2 squared. P1 plus P2 squared is S. P1 squared is M squared, P2 squared is M squared minus 2M squared. This is P1 times P2. What else do I get? I get P1 times K1. Well, P1 times K1 is, let's see, P1 and K1 appear in T. So that is minus 1 over 2 P1 minus K1 squared, because if I take that square, I will get minus 2 P1 P2. That's why I divide by 2 and multiply by 1. Of course, there are additional terms. I have minus P1 squared minus K1 squared. Again, P1 squared and K1 squared, they are both M squared, so this is minus 1 over 2 T minus 2M squared. And then I have P2 K2. Well, P2 K2 appear here again in T. And P2 K2 would be minus 1 over 2 P2 minus K2 squared minus P1 squared minus K2 squared, which is again minus 1 over 2 T minus 2M squared. And finally, I have K2 K1. This is equal to 1 over 2 K1 plus K2 squared minus K1 squared minus K2 squared, which is 1 over 2 S minus 2M squared. So now let's go back to our invariant matrix element. M is equal to I lambda squared. Now P1, P2, and P2, P1, from both of them I will get a 1 over 2, so I will get 1 over 4. Now P1, P2 is S minus 2M squared. P1, K1 is minus T minus 2M squared. Then I have K2, P2, which is again minus T minus 2M squared. And K1, K2 plus S minus 2M squared.
Where do 1 over 4 come from?
Hold on. Divided by P1 minus K2 squared is U. Well, you see, I have all these 1 over 2s. For example, when I multiply P1 and P2, I get 1 over 2 times something else. Oh, sorry, that is 1 over 2 only, not 1 over 4.
Yeah, there is no 1 over. Yeah, sure.
That's an overall 1 over 2. And then I have plus another 1 over 2. I have P1 times P2, that is S minus 2M squared. P1 times K2, okay, I hadn't calculated that, but P1 times K2 will come from U. So there is a minus sign, it will be minus 1 over 2 times U minus blah, blah, blah. So it will be minus U minus 2m squared. This is P1 times K2. I have K1 times P2, it will be the same. And I have K1 plus K2, it will be plus divided by P1 minus K1 is T, squared is T. Well, let's see, M squares will cancel. So invariant matrix element would be just I lambda over 2.
There is no actually 2 there at the end. Because 2s plus minus 2t.
I have 2s minus 2t divided by u plus 2s minus 2u divided by t, or m as a function of u, t, and s is I lambda s minus t over u plus s minus u over t. And you should also note that if I exchange u and t, it's symmetric. That will be the general behavior for the matrix elements. There are such symmetries. Okay, I know M. Now I can calculate the cross-section. And remember, the cross-section will be given by 2 pi to the 4, 4-dimensional Dirac delta of P1 plus P2 minus K1 minus K2. This is my overall energy momentum conservation. In fact, I have been using this all along. When I'm writing these equalities, I'm using the overall energy momentum conservation. And then I have my invariant matrix element squared. I have the Lorentz invariant phase space. My detector is not measuring a single value. It will be measuring some ranges. I have d cubed k1 divided by 2 pi cubed times twice e1 d cubed k2 divided by 2 pi cubed twice e2. And then I have to divide by the incoming flux, which was P1 P2 squared minus P1 squared P2 squared. So this is my cross section for this process. Now we need to evaluate these integrals, at least reduce them as much as possible. Let's look at, let's calculate it in a special reference frame, let's say in the center of mass frame. You see, my particles are coming in, and then after the collision, they will be moving in some other direction. Let's say this is my particle with momentum P1, this is my particle with momentum P2, this is my particle with momentum K1, this is my particle with momentum K2, and this is the collision region. So what are the variables that any cross-section can depend on? You see, if you look at my process, the incoming particle, the only direction they have is the collision line. What that means is I can rotate everything around this collision line and nothing should change. There's no other direction. Well, if I had, for example, fermions, spin 1/2 particles, the direction of their spin would have been another direction. And hence I wouldn't have this freedom of rotation, let's say. It can only depend on, you see, here, if you look at here, there are 6 variables left. I am already fixing the initial momentum. After the collision, in principle, I have 6 variables left, but energy momentum conservation tells me that 4 of them are already fixed. 4 of them can be determined by the initial momentum and the other 2. This gives me 4 equations. I can choose only 2 degrees of freedom for my processes. There are only 2 things that can change. But nothing should change on the rotations around the collision axis. If you define that angle phi, nothing depends on phi. So the only quantity that the cross-section can depend on, except on the initially fixed values, is this angle theta. You see, my particles, I'm already fixing the collision line. My particles can scatter in any direction. Theta can change. And the probability for scattering into a given theta can be different than the probability of scattering into a different theta. But the probability of scattering into a certain value of phi or certain other value of phi, they should be the same. So the cross-section cannot depend on the phi angle, it can only depend on the theta angle. So I should be able to express everything in terms of this theta angle. Basically, what I'm saying is I can, among these 6 integrals, without even knowing what my invariant amplitude is, I can integrate over 5 of them and just take theta as my free integration variable. So let's do that. D sigma is equal to, well, let me cancel these 3's. Oops, sorry, not 2. There is a 1 over 2 pi squared. Let me evaluate the K2 integral, which will give me Dirac delta omega 1 plus omega 2 minus E1 minus E2 m squared d cubed K1 divided by 2E1 2E2 divided by square root of P1 P2 squared minus m to the 4. Now, what else do I know? I can write spherical coordinates. D cubed K1 would be dk1 times K1 squared, and the omega, or let me write it d phi, d cosine theta. Well, phi integral, nothing depends on phi. My m squared cannot depend on phi. You see, I'm not looking at the explicit expression of my invariant amplitude. Whatever diagram, whatever processes happen, I have rotational symmetry. My initial state is rotationally symmetric around phi, so nothing can depend on phi. So whatever m is, as long as I have this rotational symmetry, it doesn't depend on phi, so I can integrate over phi. So what will it give me is 1 over 2 pi Dirac delta omega 1 plus omega 2 minus E1 minus E2 m squared dk1 k1 squared d cosine theta. Now, what else do I know? I know that energy of E1 is just K1 squared plus M squared, which tells me that E1 dE1 is actually equal to K1 dK1. So d sigma by d cosine theta is 1 over 2 pi m squared K1 times E1 times dE1. Now I can evaluate the E1 using the remaining Dirac delta function, which will give me 1 over 2 pi, 1 over the derivative with respect to E1, omega 1 plus omega 2 minus E1 minus E2, absolute value, invariant matrix element squared, and I have K1 times E1. I forgot this factor. initial flux. Now, I'm integrating over E1, but E2 also depends on E1. Remember, E2 is square root of K2 squared plus M squared. Here, K2 is the 3 momentum, not the 4 momentum. But I'm in the center of mass frame. So in the center of mass frame, K2 and K1, the 3 momentum are the same. They're just pointing in opposite directions. So this is just E1. E1 and E2, they are the same. So the sigma by the cosine theta is actually 1 over 2 pi K1 E1 M squared divided by that derivative would just give me 2. Times 1 over minus M squared. And there are other things I forgot. I have this divide by 2E1, 2E2, divided by 4E1E2, divide by 4E1E2. Here I have 8E1E2. Eight pi 2 E1 E2. Well, these E1 E2s cancel. I have 1 over 16 K1 over E1 M squared divided by this object. Now let me convert everything again back to my Mandelstam variables S, T, and U. This is, let me also write it in this way. This is the magnitude of the 3 vector, not the 4 vector K1. Divided by 16 pi E1 times M squared over, okay, what is P1? Let me just write it down first. Now, P1, P2 is 1 over 2 P1 plus P2 squared minus P1 squared minus P2 squared. So this is S over 2 minus M squared. So square root of minus M squared is actually square root of S minus 2M squared squared minus 4M squared and times 1 over 2. Or I can also write it as 1 over 2 square root of S squared minus 4M squared S So you already see that S has to be larger than 4M squared. In fact, if you use the definition of S, S is definitely larger than 4M squared at any reference frame. So d sigma by d cosine theta is 1 over 8 pi E1 K1 M squared divided by S square root of S minus 4M squared.
S orada S nasıl dışarı çıktı?
Yeah, sorry, that's square root of S. Now I still need to express K1 and E1 in terms of my variables S, T, and U. Well, let me write down my 4 momenta in the center of mass frame. Remember, on P1 is the incoming momentum, so I call that omega 1 and P. P2 is omega 2 and minus P. And in fact, they are omega 1. They have the same mass, they have the same momentum, so they have the same energy in the center of mass frame. Let me define the capital P to be P1 plus P2. This is twice omega 1 and 0. Remember, S is capital P squared, so this is 4 omega 1 squared. And keep in mind that omega 1 is square root of P squared plus M squared. So omega 1 is definitely larger than M, larger than or equal to M. So S is larger than or equal to 4M squared. So this tells me that omega 1, I can write it as square root of S over 2. Okay, this is something I will use later on. And what else can I say? K1 is E1 K. K2 is E1 minus K. But P is also K1 plus K2 because of energy momentum conservation. So this is equal to 2E1 0. And 2E1 has to be equal to 2 omega 1. E1 is equal to omega 1, which is square root of S over 2. Okay, there are many simplifications here because the particles have the same mass. If the scattered particles didn't have the same mass, well, the computation becomes a bit more complicated, but the basic idea is still there. So you just have energy momentum conservation and use energy momentum conservation to express everything in terms of things you know, or ST and U variables. So I already have E1. Now the only thing left is K1. But note that E1 squared minus K1 squared, this is M squared. So these are K1. So K1 squared is E1 squared minus M squared. Well, E1 squared is S over 4. S minus 4M squared over 4. So K1 is square root of S minus 4M squared over 2. I also know K1 in terms of my Mandelstam variables, ST and U. So let's go back. This is my expression.
So why have I, define Mandelstam variables just as a matter of calculation of convenience?
Yep. You see, Mandelstam variables are Lorentz invariant, although now I'm doing this computation in the center of mass frame. If I obtain a Lorentz invariant expression in the center of mass frame, it will be the same expression in every frame. And also to be able to understand what other people will be speaking. So they will be using these ST and U all the time, so you know what they are. For example, if you have seen any presentations by LHC or any work in LHC, they always talk about square root of S is 14 TeV. What is this? This is the initial center of mass energy. And that is the definition of S. You see, in the center of mass frame, P1 plus P2, they all have energies omega 1. In the center of mass frame, the total energy is twice omega 1. And S is nothing but the square of that one, twice omega 1 squared. So square root of S is twice omega 1. So let's continue. K1 is square root of S minus 4M squared over 2 divided by 16 pi. E1 is square root of S over 2. m squared, well, let me keep it as m squared for the time being. Still, now P1 minus P2 squared, that incident flux is this expression. So this 1 over 2 cancels this 1 over 2. Here I get a cancellation, I get an 8 pi. S minus 4m squared cancels this s minus 4m squared. Is m squared over 8 pi s. There is one thing left before you go for a break. What is cosine theta? You see, let's look at cosine theta. Let's look at this diagram. You see, cosine theta is actually P1 dot K1. So if you see P1 and K1, it will be somewhat related to P1 minus K1 squared. Let's calculate P1, which is T. Now, in the center of mass frame, just keep these expressions in your mind. T is P1 minus K1 squared. Well, this is my P1. This is my K1. So that is omega 1 minus E1 and P minus K squared. And remember, omega 1 and E1, they are the same thing. They are both square root of S over 2. This is omega 1, this is E1. They are equal. So this is actually 0. So T is minus P minus K squared. Well, you see, one thing you can immediately say is T is negative. Just like S had to be larger than 4m squared, T has to be negative. And this is a general property that from the definition of T, T is always negative in the scattering process. Well, let's see, this will be equal to minus P squared minus K squared plus 2pk. But this tells me one more thing. The magnitude of P and magnitude of K, they are equal. So this T is equal to minus twice P squared 1 minus cosine theta. You see, their energy doesn't change. It's just the direction of the scattering particles change. Energy doesn't change. So, but if their energies are the same, the magnitudes of their momentum are the same. It's just the momentum has changed direction without changing magnitude. So this tells me this is equal to, now what was K1? Their momentum is S minus 4m squared over thing, so over 2. So there's a 2 over here. This is minus square root of S minus 4m squared 1 minus cosine theta. For this process, this is my T. What is dt? Well, dt is square root of S minus 4m squared ds. Oh, sorry, you are right. Then I also have a 1 over 2. Because, you see, k is s minus 4m squared over 2. When I take the square, it's 1 over 4. Here I have a 2, so it becomes 1 over 2. d cosine theta. So I can just use this expression to replace cosine theta. So d sigma by, well, d cosine theta is twice dt divided by s minus m squared, d sigma divided by 2 over s minus 4m squared, dt is equal to m squared over 8 pi s. So d sigma over dt is s minus 4m squared divided by 2 pi s. Invariant matrix squared is just this thing squared. So this is my invariant cross-section as a function of t. Scattering cross-section as a function of t.
S and U do not depend on T.
Well, you see, you can think of u is, t is cosine theta. So S definitely doesn't depend on cosine theta, S only depends on the initial particles.
I see.
But U will depend on, U is P1 minus K2. So U will depend on this angle over there.
Yeah.
But that angle is theta. So U also depends on theta,
Yeah.
cosine theta. But that means U depends on T. In fact, let's do this exercise. S plus T plus U. S is P1 plus P2 squared. T is P1 minus K1 squared. U is P1 minus K2 squared. Or let me write it as P2 minus K1. Well, this is P1 squared plus P2 squared plus twice P1 P2 plus P1 squared plus K1 squared minus 2 P1 K1 plus P2 squared plus K1 squared minus twice P2 K1. This is, well, these two are both m squared. These two are m squared. So I get 4m squared. Here I have a P1, P2. Well, let me just, I have this term, these three terms. Twice P1, P2 minus K1. Minus twice P2 times K1. Well, okay, if you play around a bit, I don't see it straight away now, this will be just 4m squared.
There's also T squared and K squared right over there. On the left, on the right. 6, right? It has 6, right?
There are 6, yes. When you play with the kinematics a bit, you will see that S plus T plus U is actually 4m squared.
So S is a constant for us.
S is constant, so T and U, they depend on each other. They should depend on each other.
We said that the sigma over d cos theta is m squared over 8 pi s.
Mm-hmm.
Then you wrote 4 pi s.
Any questions?
I have a question, but it's unrelated to this. Is our photon propagator need not be gauge invariant object?
No. Propagators are gauge-dependent objects.
Okay, so only the matrix element. has to be-
Physically measurable quantities have to be gauge invariant. You see, when we define the propagators, let's say even the scalar propagator is not gauge invariant. This is how we define the propagator. Under a gauge transformation, this just becomes it's not gauge invariant. It changes. But propagators are not things that we actually observe.
So if we prove the, not prove, but at least for the, for this diagram or the second order diagram, that we have the word identity, can we say that for the entire matrix element?
No.
So are we able to derive the word identity
Well,
in scalar QED?
We can. It will take a bit more work. It has to satisfy. I mean, you see, it might happen that quantization breaks your gauge symmetry. Classically, we have the gauge symmetry, but when we quantize it, it might. We have certain symmetries, not gauge symmetry, certain global symmetries, that when we quantize at the classical level, when we quantize the theory, that symmetry no longer exists. Those are what we call anomalous symmetries. They exist classically, but quantization procedure itself breaks them. But gauge symmetries are not so. That is not this one. You cannot gauge a theory that is anomalous. Is the endpoint function gauge invariant? No, you see. But the thing is, if you look at this matrix element, it's not gauge invariant. You see, when we are looking at S matrix element, what we are calculating an endpoint function. If we are just looking at the scattering of scalars, we are looking at the 4-point function. And that 4-point function, I can guarantee you that it is not gauge invariant. But we are not measuring the matrix element itself. We are measuring its absolute squared. But you see, just look at this two-point function. It's not gauge invariant, but its absolute value is gauge invariant because the difference is just a phase with norm 1. And hence scattering cross sections, etc., will be gauge invariant. But the matrix elements are not. They don't have to be. So let's give our 10-minute break and we will meet in 10 minutes.